Welcome to the start of Chapter 4. Chapter 4, we're going to start with the concepts of probability and counting rules. So, when we're talking about probability is actually a different branch of mathematics than statistics, technically. So there's separate branches of mathematics, the same as, say, algebra and geometry are separate branches of mathematics. So when you talk about mathematics, there's different types of mathematics. There's algebra, there's trigonometry, there is geometry, which some would argue that trigonometry is a branch of geometry, but we won't get into that right now. There's statistics, there's probability, and so these are all subsets of the main concept or the main core discipline of mathematics. Now, there's lots more. There's so many branches of mathematics, but just so that we get an idea of what's going on. So you might say, well, when I'm in a class that's called Elementary Statistics or Introduction to Statistics, why are we studying a different branch of mathematics? Well, the reason is because statistics and probability, while technically two separate branches of mathematics, are really inherently linked to each other. And they're very typically taught together. Most Introduction to Statistics class will have some basic probability. And the reason that they're taught together is because the probability provides like a framework for understanding the ideas of uncertainty, randomness, and those are both really important, essential building blocks to statistical analysis, which we're going to be talking about when we get to Chapter 6. We'll start doing some statistical analysis. So that understanding of basic probability is necessary to kind of understand the foundations of statistics. So our first section here in Chapter 4 is on sample spaces and probability. And our learning objectives are to determine sample spaces and find the probability of an event using classical or empirical probability. Of course, these are all terms we're going to have to learn what they mean. So we have classical probability, we have empirical probability, and within those we're going to learn how to find the probability of a simple event and then how to determine sample spaces. So we're going to start off with sample spaces. So we're going to start with, the first thing we're going to talk about is what probability and outcomes mean, and then we'll get into the sample spaces. So probability of an event is the chance of the event occurring. When we're doing a probability experiment, that is the process involving chance that leads to well-defined results called outcomes. So rolling a die, flipping a coin, drawing a name out of a hat, those are all probability experiments. You think about, taking a water bottle and flipping it and wanting it to land on its base. That's a probability experiment. The outcome is the result of a single trial of a probability experiment. So one time of flipping the coin or one time of rolling the dice, either one die or two dice or more, would be considered a single trial. But if you record it as one event happening, then that is an outcome. So for example, flipping a coin and recording if it comes up heads or tails is a probability experiment. The possible outcomes are heads or tails. And then the sample space is the set of all possible outcomes of a probability experiment. So when we are doing a probability experiment and we flip that coin, the sample space for that experiment is either heads or tails. The sample space for rolling 2 dice would be all of these different combinations. You could have a 1 and a 1, a 1 and a 2, a 1 and a 3, so this is all column. This column has the second die as 1, and then this first row has the first die as 1, 2, 3, 4, 5, and 6. So all of these down this row would be 1 on the first die, and then all the variations on the second die, 1, 2, 3, 4, 5, or 6. This would be a 2, and then all the different possibilities to go along with the 2. A 2 and a 1, a 2 and a 2, a 2 and a 3, and so on. And that all 36 possibilities are the sample space. And you can show the sample space with a picture like this, or we could write it out. We could say the sample space for flipping a die is 1, 1, 1, 2, 1, 3, and we could continue all the way up until we got to 6, 6. But a lot of times, if it's something like this that's real visual, it's nice to see it in picture form like this, so you can, so your brain can understand it more quickly. Now, one way to determine all the different elements in a sample space is to draw a tree diagram. So let's say we have a box, and in the box there's 1 blue golf ball and 1 red golf ball, and we put the golf ball back after each draw. So in the game, the player draws one of the balls out, then it puts it back, draws the next one out, puts it back, draws the next one out, puts it back. So each time they have an equal chance of getting either blue or red. And it wouldn't even have to be equal chances. There could be 2 blues and a red. This still would have the same sample space that it could either be blue or red. So we could use a tree diagram to find all the possible combinations of draws. So we start with, well, what can the first draw be? Well, the first draw can be blue or red. And then after the first blue, if you drew blue the first time, you could then on the next one get a blue or a red. And then once you drew a blue and a blue, then on the next one you could do a blue or a red. And we could follow that through for all the different possibilities. So here we would have blue, then a red, and then a blue and a red. So if we put off to the side what branches, what colors the branches lead us through. So in this case, blue, 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 we get one of the things in the sample space. So blue, blue, blue is one of the things in the sample space. Blue, blue, red would be another possibility in the sample space, and so on and so forth. So in this case, there's 8 different things in the sample space, 8 different possibilities for those 3 draws. So obviously, we probably don't want to draw a tree diagram every time. So let me kind of show you a method when you're going through these to kind of think through, do I have all the possibilities? So with something like this, and when it gets too big, it's really pretty hard to do it like this. But if it's like 3 or smaller, you can usually do the method that I'm showing you. So if we start with blue, 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 and then the next thing we want to do is we want to add in 1 red. And I always think of this red as shifting places. So the red could be the last draw, or the red could be the middle draw, or the red could be the first draw. So the red just shifted from the end to the middle and then to the front. So we still have 2 blues and 1 red, but they're just in all the different possible locations. Well, then we could also have 2 reds with 1 blue. And then the blue can shift places like the red did. So the blue could be in the middle, or the blue could be the first draw. And then our last final option is that they're all red. So we start with all blue, then we add in, these three are just one red for these three. And then these three are two red, or one blue, however you want to call it. And then we end up with all red. So all blue to all red, add in one red, add in two reds, and then finish with all three reds. So a way to kind of keep track of it. All right. So the outcome, as we mentioned, is the result of a single trial of an experiment. For example, rolling a 2. But an event is the set of outcomes of the entire probability experiment. So there's two different types of events. If you only have one outcome, such as a fair die is rolled once and you got a 2, and that's the entire probability experiment, then that is called a simple event. But oftentimes we don't have just one trial. So an event that combines more than one simple event, such as a fair die is rolled 10 times and we got 2, then a 4, then a 4, then a 1, then a 6, then a 5, then a 2, then a 5, then a 1, then a 3. Or a die is rolled and a coin is flipped, and on the die we got a 4 and on the coin we got a heads. Those are called compound events. So when you take several simple events and put them together as as one probability experiment, then those are compound events. So when the event combines more than one simple event, then you're going to get a compound event. Okay, so when we're talking about classical probability, there's actually, I'm going to list out here, there's actually 3 different types of probability. There's classical probability, there's empirical probability, and there's subjective probability. Now, the first type, classical probability, is probably what most people think of when they think of of probability. This is where you have, dice, coins, drawings, anything that you can kind of represent with a physical entity, and you know that you can look at what you have and determine what the likelihood of that happening is. So when you look at a dice, or when you look at a single die, you know that that die could have a 1 or a 2 or a 3 or a 4 or a 5 or a 6, and you know they're all equally likely because unless if the die is fair, each of those has an equally likely chance of happening. Same thing, if you have a fair coin, you have your heads and your tails, and they have an equal chance of happening. Drawings, that would kind of depend on if, something in the drawing could be entered more than once, but we could still, by looking at what's in the drawing, determine the probability of any of those things occurring. So that's classical probability. Empirical probability is when you use data from either research or a survey, which is actually a type of research, or some other kind of study, and you use the data from that to figure out probabilities. Empirical and classical actually behave very similarly when you're doing the work for them, but they are technically different things because the empirical is from research that's not as, research and studies and surveys are not as exact as, say, classical with its dice and coins. And then subjective is very fuzzy. Subjective is when the probabilities are determined by the expertise or beliefs or some other past experience of a person. And so subjective probability are things like weather. Now, that's not just, a guess. They do use data and facts, but it's still very subjective as to how those are analyzed. So you might see on, 2 different websites, 2 different television stations, you might see a different percentage for the chance of rain. Other places that this would be used would be in betting, like in sports betting, the probability of a team winning. And another real common example that's given is like stock markets. Should I buy? Should I sell? Is this going to go up? Is this going to go down? Nobody's really certain. It's all subjective and based on a person's personal judgment, their past experiences, some empirical data that they have, but it's very inexact. So we're going to start off, which makes a lot of sense, with what we consider to be kind of the hallmark of probability, which is classical probability. And in classical probability, we have a sample space to determine the numerical probability that the event will happen. So again, our dice, our drawings, our coins, things like that. We assume that all the outcomes in the sample space are equally likely events. So when we're talking about a drawing, again, in the drawing, you might have person A, person B, and then let's say even it's allowed that person C could get their name in twice into the drawing. And you're drawing, out of this box or hat or bag or whatever. But we still have equally likely events because it is equally likely that we will draw A as B as the first C entry as the second C entry. So even though overall there's a better chance for C, one of the C's to be drawn, there's still an equally likely chance that the first C entry will be drawn as the second C entry will be drawn and the B and the A. So each of those would have a 1/4 chance. So when we're talking about a coin flip, there's 2 equally likely outcomes and each has a probability of 1/2. 2 outcomes, heads is 1/2 chance, tails is 1/2 chance. A die has 6 equally likely outcomes. Each of those has a 1/6 chance. So you have a 1/6 chance of rolling a 1, a 1/6 chance of rolling a 2, a 1/6 chance of rolling a 3, and so on. So in classical probability, in general, the probability of an event occurring is the number of those events, those successful outcomes that we want, over the total number of outcomes in the sample space. So if we look at, say, the die, you could say, what's the probability that we're going to roll a 5? Well, there's 1 5 on the die, and there's 6 sides to the die. So there's a 1/6 chance of rolling a 5. And probability should always be expressed as reduced fractions or as decimals, rounded to 3 decimal places. What's magic about 3 decimal places? It's not really magic, but the reason we do that is because, say, your decimal comes out to be 3671332, and it keeps going after that. If we round to 3 decimal places, so we round to the 7. So in this case, after the 7 is a 1, so we're going to leave it 7. So we'd say that's approximately 0.367. And what's nice about that is then if we also want to write that as a percentage, we get 1 decimal for our percentage. So that's pretty common practice. So 36.7% or 0.367. If you have a really, really small, we don't really deal with these a lot, but if you do have a really small probability and it has multiple zeros in front of it before it gets to a non-zero digit, it is okay to go to that non-zero digit and not write that the probability is 0.000. So let's say we had something that came out with a probability of 0.0000314. It's the appropriate thing to do with that then is to say it's approximately 0.00003. Just keep going until you get to a digit that's not 0. All right, so let's do a classical probability example that's different than the rolling a die or flipping a coin. So we have our game that we talked about where you're going to draw 3 times out of the box, and there are 2 golf balls in there, one red and one blue, that gets put back each time. So this was our sample set, if we remember. Okay, so here's our sample set. There were 8 things that could happen. And so in the classical probability point of view, each of these outcomes is equally likely. And so the probability of each is 1/8, or if we do 1 divided by 8 on the calculator, that comes out to be 0.125. So this is a good time to talk about how to do fractions on your calculator too, because you don't want to do all these fractions by hand. This class is not about do you know how to reduce fractions, add fractions, but we're going to be working a lot with the fractions. So you've already passed that class. That class was a prior class at some point in your life. And so whether you're comfortable with fractions or you're not comfortable with fractions, that's not what this class is about. So what we want to do is make sure that you are comfortable with getting these in your calculator correctly. So if we take this problem, for example, what did it do? Okay, so we had 1/8, and we wanted to switch that to a decimal. So there's a couple different ways we can do this. We can do 1 divided by 8, and it will give it to us as a decimal. Or we can use our fraction button. Now this is pretty similar to what you see on the Casio calculators. It's just on the Casio calculators, instead of saying N/D on the button, it'll have like a box over a box. But the process is pretty similar. So on the Casio calculators, what you see right here, the box over the box, that's what they have on the button instead of the N and the D. All right, so I'm going to put in a 1, and then I'm going to either arrow down or I think that's the only way to do it. Yeah, so we're going to arrow down, and we're going to put in the 8. Now we're going to hit enter, and it's going to tell us 1/8 is 1/8, which isn't really what we want. What we want is we want it as a decimal. So we're going to hit, on this calculator, we're going to hit second, and then this F to D button. And I had to hit second because it was in green at the top of the button. That means I have to hit the second first, the shift button. And then I hit enter, and it switches it to 0.125. Now it works both ways. If you get a decimal answer and you'd really like it as a fraction, you just hit second and that button again and hit enter, and it'll switch it back to a fraction, or switch it to a fraction if it wasn't a fraction. Now on the TI calculators, the button for that, and almost always on the Casio calculators, I might have just said TI, I meant Casio. Almost always on the Casio calculators, it'll give you like an exact answer. So it'll give you, oftentimes it'll give you the fraction when you really just wanted the decimal. And the button on there doesn't say F to D, it says S to D. So you'll find a button on your Casio calculator that looks something like this. It's an S, and then it has like a 2-way arrow, and then a D. If you just push that button, if your answer is showing as 1/8, hit that button, and it'll show you that that's 0.125. If it's a repeating decimal, sometimes what it'll do, like for 1/3, it'll say 1/3. If you hit the button once, it'll give you 0.0333, a whole bunch of decimals out. That was a weird 3. Try that again. And so on. And then if you hit it again, oftentimes it'll give like this. It depends on the model that you have, but it'll give you all three versions. So then you have to hit it a third time to get back to the 1/3. So it'll show 1/3, hit it once, it'll give you 0.33333. Hit it another time, you'll get 0.3 with a bar over it, and then hit it again, you'll get 1/3. Okay, so you definitely want to be able to find that fraction button on your calculator. It's either going to look like this one calculator had the N over the D, or it's going to have like a box over a box, and you just fill in the boxes. So let's look at another probability example. I guess we actually haven't gotten to an example yet, except for the likelihood of any one of those things happening. So what if they said, instead of, any one of those things happening, let's say our question is, what's the probability that you get a draw that has two reds in it? So we're going to look up at our possibilities. So our event, we want to know the probability that we get two red. Now it doesn't specify where those two red have to be. So that could be this situation right here where you get red, red, blue. It could be this situation where you get red, blue, red, or it could be this situation where you get blue, red, red. So all three of those have two reds in them. Now it says exactly two red, so we can't count red, red, red because that has three red. If it said two red or more, then we could count the one that has all red. But this one just said exactly two red. So either getting a red, then a blue, or a red with a blue in the middle and a red at the end, or a blue and then two reds after that. All three of those meet the criteria. So if we look at, we're supposed to do the number of what we want. So in this case, there are three of what we're looking for. There are three that have two reds in them out of the entire sample space, which is 8. So 3 out of 8 chance, a 3/8 chance that we're going to get two reds in our 3 draws. Now if we again do that on the calculator, clear this out, we could either do 3 divided by 8, or we could do the fraction button and put 3 over 8, and then switch that to a decimal. So 3/8 or 0.375. Or, again, technically, we could say all of these are appropriate, and as far as like on a test or something like that, I don't care which version you have it in. Whatever's easiest for you. And Alex usually tells you what version they want it in. So in this case, you could put 1/8, you could put 0.125, or it would be completely appropriate to say 12.5% probability. In this case, 3/8, 0.375, or 37.5% probability. Any of those are valid and perfectly okay ways to leave your final answer. But again, I think on Alex, they almost always specify as a reduced fraction or a decimal to 3 places. Okay, so let's look at some rules of probability. The probability of any event occurring is a number, whether you write it as a fraction or a decimal, that is between 0 and 1. So in other words, 0 is the smallest probability, all the way up to 1. So what this means is you have 0 on one end, and that is less than or equal to the probability of any event, which is less than or equal to 1. So probability of an event has to be somewhere between 0 and 1. The sum of the probabilities of all the outcomes in a sample space is 1. For example, if you consider rolling a fair die. So if we add up all the probabilities in this case, so a 1/6 of the first one, plus a 1/6 of the second one, plus a 1/6 chance of a 3, plus a 1/6 chance of a 4, and so on. If we add those all up, 1 6 plus 1 6 plus 1 6 plus 1 6 plus 1 6 is 6 6, which is 1. And that is always true, that the sum of all the outcomes of a sample space is going to total to 1. And then if an event cannot occur, that is a probability of 0. So this is the beginning. This means that the event cannot occur. And then 1 means it is for certain. Okay, it must occur. So let's look at some examples of that. The example, or the probability of rolling a 7 on a single fair die is 0, because there's no 7 on the die. So if this is our just regular standard die, and it's numbered from 1 to 6, then the probability of rolling a 7 on that die is equal to 0. There's no way that you could ever get a 7 on that if there's not a 7 on one of the sides. Then if we go to the other end, sometimes an event could be for certain. So if we look at our die again, the probability when you roll that die that you're going to get a number that is less than 10 is absolutely for certain, because every number on that die is less than 10. So 1, 2, 3, 4, 5, 6 are the only possible outcomes. Those are all less than 10. So the probability of rolling something less than 10. And we're not talking about rolling it twice. We're just talking about rolling it one time. So the probability of rolling it one time and getting a 7 is 0. The probability of rolling it one time and getting a number less than 10 is 1. Absolutely has to happen. This absolutely cannot happen. And then this absolutely must happen. All right, so those are some general rules. And then we have kind of a visualization of it. I kind of did it up above, but if you have a, your far end of your probability visualization, 0 means it cannot occur. If you're below half, then we would probably say it's not likely to occur. If you were above half, you would say, well, it's probably likely to occur. If it's right in the middle, if it has a probability of 0.5, then it's equally likely to occur as to not occur. Like, what's my probability that I'm going to roll or flip a heads when I flip a coin? 1/2, or 0.5, or 50%, meaning that I'm equally likely to get a heads as I am a tails. So the probability of a heads is 1/2. May or may not occur, equally likely that it will as it won't. And then, of course, the 1 is certain to occur or must occur. So now we're going to talk about complementary events. Sometimes when we're working out problems, using the idea of complementary events it makes the problem easier. So the complement of an event is the set of all outcomes in the sample space that are not the event E. So for instance, and informally, the complement of E, well, formally it's denoted E with a bar over it, and that's often read as not E. So this is E, and then this is not E. Okay. I don't like the way that looks. Hold on a second. So this is just read, of course, E or event. And then this means informally not E or not the event. And informally, the complement of event E is that E does not occur. For example, if we think about rolling an even number on a fair die, the complement of that would be rolling an odd. So the rolling an even, that would mean, a 2, 4, or 6. And then not even would be 1, 3, 5, which we could also call the odds. Sometimes you can name them different ways. So not even is the same thing as saying odds. And if we put those two probabilities together, they have to always total 1. So the probability of an event occurring and the probability of an event not occurring is 1. Because remember, the sum of all the probabilities have to add to 1. And so if we're taking everything that is the event and we're adding it to all the things that are not the event, that's also going to total up to 1. And you can think of it as two ways. You can think of it as they add up to 1, or you could think of it as the probability of the event is 1 minus the probability of not the event, or technically you could think of it as, we don't do this as often, probability of not the event is 1 minus probability of the event. But the reason that it's only written the one way here is because typically what we do is we calculate the not E because it's easier to calculate sometimes, and then what we're looking for is E. And so we'll calculate this, subtract it from 1, and then that will get us our P of E that we're looking for. So let's look at some examples of this. We've got, from our blue and red golf ball game, we can look to the sample space to find the probability that at least one draw is a red. So we can look at this and say, okay, well, what's the probability that at least one is a red? Well, we have this one, we have this one, we have this one. Again, it's at least, so it could be 2 or it could be 3. So all of these. And we could say, oh, well, there's 7 different things that could happen. And so the probability of at least one red is equal to the 7 ways that you could get at least one red out of the 8 in the sample space. But most of you, maybe not most, but a lot of you probably in your head thought to yourself, well, why are we counting those 7 when I could just look at the fact that there's one that isn't what we're looking for, that doesn't have any reds. And so instead of thinking of it as 7 eighths right off the bat, you might say, well, one of them doesn't meet the criteria. So the probability that I don't get a red is 1 out of 8. And I could just subtract that from 1 and get 1 minus the probability of no red. I'm going to rewrite this because this probably, with the decimals, isn't how most folks would think of it. So the probability of no red is 1/8. And so then the probability of at least one red, I'm going to put some red just to save space here, would be equal to 1 minus 1/8, which is 7/8. And then, of course, the 7/8 is equal to 0.875, or 87.5%. Okay, so, but the two together, if we say, what's the probability of a red, what's the probability of no reds, together those have to total up to 1 because the sum of all the possibilities has to add up to 1. So now we're going to look at a couple with empirical probability. Now, empirical probability, as I mentioned before, it actually acts a lot like the classical probability. It's just that our information, instead of looking at something solid like a die or a coin, we're going to be looking at something from a survey. So empirical probability, instead of assuming all outcomes are equally likely, the probability is deduced from actual data collection. As we mentioned, a survey, a study, an experiment, and then we record. And so in order to get that empirical probability, this looks a lot like classical, we have the frequency of the event rather than the number of the event over the total frequencies in the distribution. So here's a sample. If somebody sampled 60 people on a campus and recorded that there were 22 students that walked by them that had brown hair, 15 that walked by them that had blonde, 18 that had black hair, and 5 that had red hair. Then we could assume that the probability that someone on that campus having brown hair is roughly 22 out of 60. So total was 60 people. That's where we get the number on the bottom. That was the total in the survey, or total in the sample. And this was the number that had brown. And then if we reduce that, we could write it as 11/30ths. And then that could be changed to approximately 0.367 or 36.7%. Let me pull the calculator up since that's the first one that we've done that didn't come out with a fraction that was already reduced. So we've got 22 out of 60. If we type that into the calculator, and if you want to know, well, is that reduced or not? Again, this class isn't about, can you do the fractions by hand? If you can, great, that's fine. But if you're not super comfortable with it, put it in as a fraction on your calculator and then hit enter. If it can be reduced, the calculator will reduce it. And then again, we can use the F to D button to change it to a decimal. Now you notice here that this has 0.3666666. I'm not sure what this one does. Let me see if it'll write it with a bar, or if it'll just go back to, no, this one just goes back to the fraction. So the 0.3666, it's actually, the sixes go on forever. They just round the last decimal to a 7. But still, we get approximately 0.367 because we're going to round this to the third decimal spot, which would be 366. But then after that 6, there's another 6, so we have to round the 6 up to a 7. Okay. And then that would be 36.7%. And then the probability that a person has blonde hair, you could estimate that the population has about a 25% chance if you randomly select a student. The probability that they would have blonde hair, we could estimate it would be about the same as our sample, which was 15 out of 60, which is 1/4 or 0.25 or 25%. Again, if we type that on our calculator, we're going to get 15 out of 60, hit enter, and then if we want to switch it to the decimal, we just hit that button and hit enter again. So 1/4 or 0.25. Okay, so one of the last things we're going to do here, yes, we have just a couple little more concepts here for 4.1. The first thing, this first slide out of these last two is talking about the law of large numbers. So here's the scenario. If we flipped a coin 20 times and we got 8 heads and 12 tails, that would show from that empirical study that the probability of heads was 40%, probability of tails was 60%. We know that that's not the truth classically of a fair coin. So why did we get 40% and 60%? Well, because of the small sample, we aren't going to necessarily get the true theoretical probability. But let's say we flip that coin, instead of flipping it 20 times and getting 8 and 12, let's say we flipped it 1,000 times. Well, we still might not get 500 and 500, which is what the theoretical probability says, but we would probably be a whole lot closer than 40% and 60%. It'd be very unlikely that we would get 400 heads, let's say, and 600 tails. That would be surprising. Then we'd start questioning, is that coin actually a fair coin? that would probably be pretty convincing evidence that it wasn't. So we may not end up exactly 500 to 500, but we would expect that we would be much closer to 50-50 than we were with the 40% and 60% when we just flipped it 20 times. And so if the coin is fair, if the heads and tails are equally likely, it's a fair coin, then the more we flip the coin, the closer to this theoretical probability we would get. So 1,000 times, 10,000 times, 1,000,000 times, you would get closer and closer to that 1/2 chance of each, 50% and 50%. And this is what's known as the law of large numbers. And it says that the empirical probability of an outcome will approach, so the empirical probability is the actual trials, and it will approach the theoretical or the classical probability as you do more trials. More trials, you'll get closer to that theoretical probability. And then we talked briefly about subjective probability. Subjective probability is just probability based on an educated guess or an estimate. You're employing opinions, inexact information. And so with those, we just make an educated guess about the chance that an event will occur. So a weather forecaster might say there's 80% chance of rain based on current weather conditions and how likely rain was after similar conditions in the past. Because weather's never exactly the same. When setting betting odds in sports, bookmakers must make a subjective decision so that they know how to set the odds so that they have a better chance of winning than losing. Because the bookmaker is always going to make it so that they have more of a chance of winning than the person placing the bet. That's their goal anyway. When your flight is delayed, this one's kind of a funny one, you might make a subjective decision about the probability that the plane will start boarding before you can run off to buy a piece of pizza and get back to the gate. So let's say you're in the first group and you really want to be back when the first group starts to board. And you're like, okay, we have a delay. They haven't given us the exact time. I think I can run over here and grab a piece of pizza and get back before the plane starts to board. You're making a subjective decision. You're saying, I think I have a chance. I think I have the probability that I can get this done before I get back. The biggest problem with subjective probability in a day-to-day life probably would be the idea that if you have an incorrect belief about the probability of an event, that could cause you to make an incorrect decision. That could be regarding finances, regarding health, regarding relationships. You might make a bad judgment call. You thought that the probability that if you were just 5 minutes late to your interview, that it wouldn't affect your chances of getting the job. And you were wrong. And you didn't get the job. Well, that would affect your finances. You thought that next week it was a pretty good chance that you would get 40 hours plus 10 hours of overtime, and so you spent money expecting that to happen, and it didn't happen. Then that could affect your finances. Same thing with health. Oh, it won't hurt if I just this one time eat this one thing that doesn't treat me well, or don't take my medication, or things like that. It won't hurt anything. And if you make a mistake, it could affect your health. So that is it for 4.1. And we're going to go ahead and do 4.2 on this video. And then we'll cut this video off. But the next section is kind of short. So we have still, of course, probability and counting rules is what we're talking about in Chapter 4. And this section we're going to talk about what's called the addition rule for probability. So section 4.2. And our only learning objective is to find the probability of compound events. We talked about compound events. That's when you have more than one trial in your probability experiment. And we're going to be using what are called the addition rules of probability. Our first term that we're going to learn in this section is the term mutually exclusive. So two events are mutually exclusive events, or sometimes called disjoint events, but honestly, mutually exclusive is used much more often. Mutually exclusive events if they cannot occur at the same time. Now think of everyday language. I always try to reference you back to that so you can remember what things mean. Mutually exclusive in everyday language usually applies to a relationship. When two people are in a mutually exclusive relationship, that means that they don't have another relationship occurring at the same time. So, mutually exclusive events, like a mutually exclusive relationship, means that the two events cannot occur at the same time. So they don't have anything, there's no way you could have both of those outcomes at the same time. So let's look at some examples here. A randomly chosen student is an engineering major, and a randomly chosen student is a junior. So the question is, are these mutually exclusive, or could they occur at the same time? So our engineering major and junior, could those occur at the same time? They could. And because they could, then they are not mutually exclusive. A student could be an engineering major and a junior, so engineering and being a junior are not mutually exclusive. And then when we look at a deck of cards, if we look at this deck of cards, a randomly chosen card is a 5, and a randomly chosen card is a jack. Could those happen at the same time? They could not. The 5s are here. The jacks are here. They do not overlap each other. There's no cards that are both a 5 and a jack. And so randomly chosen 5, randomly chosen jack are mutually exclusive events because a card cannot be both a 5 and a jack. And why is that important? Well, if we have two events that are mutually exclusive and we want to know the probability of one or the other occurring, or B, then if they are mutually exclusive, if they have no overlap between them, we can just take the probability of A occurring plus the probability of B occurring. So let's do that with the cards. By the way, they use cards a lot in the homework, and I'll use it in examples. If you have a deck of cards problem on the exam, I will put a picture of it on the exam because I know not everybody plays cards on a regular basis, doesn't know how cards, the makeup of the cards. Other people know them very well, play cards with their family or their friends. Other people just don't. And so I don't want to assume that you know a deck of cards. The reason we use a deck of cards is just because it's got a lot of different ways we could look at it, because we can look at suits, we can look at colors, we can look at the number. And so if you need that on your homework, feel free to please pull up a picture on your computer. So just type in sample space cards and you'll get all kinds of different pictures of it. So just grab whatever one you like. I actually kind of like one like this because it's not so busy, but maybe you like the one like I have on here where it's got the actual pictures of it. But something to help you visualize it is perfectly fine. And if you need it on the exam, I'll have it on the exam. So the one thing also that people get a little bit confused, and I'll show it on the one that we have, is they'll sometimes talk about face cards, and people will often think that the ace belongs with the face cards, but it does not. The face cards are literally the cards that have faces on them. So the jack, the queen, and the king. So there's a jack, queen, and king of spades, clubs, hearts, and diamonds. Also, this really shouldn't matter, but if you have a hard time remembering the suits, the club is the one that kind of looks like a 4-leaf clover. And the reason it's called a club is because it sort of looks like an old-fashioned club with, like, from medieval times that you would like wallop somebody with. And then the spade is the one that looks like an upside down heart with, kind of a little, looks like a leaf maybe. And that's called a spade because it kind of looks like a shovel, like a spade. And then, of course, hearts and diamonds are pretty recognizable. So clubs is the one that looks like a medieval club. Spades is the one that looks like a little shovel, like a spade. And then hearts and diamonds. And spades and clubs are black. And then hearts and diamonds are red. Okay, so enough of that. So what I want to do here is use this rule to determine the probability that we are either a 5 or a jack. So because they're mutually exclusive, I can just use the mutually exclusive events addition rule 1. So the probability that you draw a 5 or a jack, whatever the case may be, you have a hand where getting a 5 or a jack would be helpful. Because they're mutually exclusive, you can just take the probability of getting a 5 and add it to the probability of getting a jack. So the probability of getting a 5, there's 4 5s out of 52. And then the probability of a jack, there's 4 jacks out of 52. So the probability of getting a 5 or a jack is 8 out of 52. We take that and do it on our calculator. 8 out of 52 gets us 2/13, which if we change that to a decimal is approximately 0.154. So 2/13 or 0.154. Let me double check I wrote that right. Yes, 2/13 or 0.154. All right, so let's look at another example of this. Another couple examples, actually. In a group of students, 22% say their favorite ice cream is vanilla. So if we're talking about favorite, that usually indicates they're just getting one selection. So 22% say their favorite ice cream is vanilla, 65% say their favorite is chocolate, 13% say their favorite is strawberry. So what's the probability that a randomly selected student prefers vanilla or strawberry? Well, first of all, we have to realize or make sure that these are mutually exclusive events. And they are. If they're only allowed to pick one, then a student is either going to only pick vanilla or strawberry. They're not going to pick both. So vanilla, favorite strawberry, mutually exclusive. Since they're mutually exclusive, to get the probability of vanilla or strawberry, we can just take the probability of vanilla and add it to the probability of strawberry. So in this case, they're in percentages, so we can just take 22% plus the 13%, so 22% for vanilla, 13% for strawberry, and we get 35%. Which we could switch to a decimal or a fraction, but it's usually not yet necessary. If they start the problem with percentages, they almost always will just stick with percentages. Okay, so now let's look at the second example of using addition rule 2. Students from a high school are polled, that should be students, from a high school are polled about how they get to school in the morning on most days. The following two-way table displays the results. Again, it says on most days. So a student is not going to be able to pick two things. What is the probability that a randomly selected student rides the bus or walks bikes? Okay. So here are the bus folks, and here are the walking or biking folks. Now this is what's known as a two-way table. So if you look at this, each cell means something different. So like this 35 are the seniors who ride the bus. The 60 are the seniors who ride in a car. So car and seniors, and so on. So when we're looking at this, the bottom number here is the total. So 105 is the total of the 35 seniors that ride the bus and the 70 juniors that ride the bus. Same thing over here. You've got your walkers and bikers. There are 5 seniors and 10 juniors. So total, that's 15 students that answered that most days they get to school by walking or biking. These are mutually exclusive events. We were told that there was 200 in the survey total. So you have your 105. Let me back up here. So the probability that you're going to be on the bus or you're going to be a walker biker is the probability that you ride the bus, that the student rides the bus, plus the probability that they were a walker biker. Okay, so the probability that you rode the bus was 105 students out of 200. The probability that a student rode or walked or biked was 15 students out of the 200. And so altogether that's 120 out of 200 students. If we reduce that, if we do 120 divided by 200 or put it in as a fraction and reduce it, we didn't write the reduced fraction here. It would be 3/5 would be the reduced fraction. So 3/5 or 0.6 or 60% would all be appropriate. So 3/5 of the students either rode the bus or walked or biked. Now we could use the complement and we could say, oh, well, if we know that, if we know 60% were in this category or this category, that means that for the car, that must be 40% because that's everything. So if there's a 40% chance that they're one of these two things, that means, 60% that they're one of these two things, that means that there's a 40% chance they're in the leftover category. That wasn't asked on this question. I was just going above and beyond. Okay, so now we're going to look at addition rule 2. And addition rule 2 covers the occurrence of non-mutually exclusive events. And the problem with non-mutually exclusive events is that they overlap. And the sum of the probabilities of both events gets counted in that overlap twice if you just add them together. So, of cars at a sales lot, for instance, let's say 30% are white and 25% have sunroofs. If I were just to say what's the probability that a car is white or has a sunroof, then I would get 30 plus 25%, which would be 55%. But that's not necessarily true because a car being white and a car having a sunroof are not mutually exclusive events. We would have to know how many cars are white with a sunroof so that we don't count them in the white cars and in the sunroof cars. So the probability of this, of having a white or a sunroof, is going to be the 30% plus the 25%, but then we have to subtract out the 10% that got counted twice. So this 10% got counted in the 30% and it also got counted in the 25%. So I have to subtract it out so that it doesn't get double counted. So instead of there being 55%, it's actually 30 plus 25 is 55 minus 10. It's actually only 45% of the cars are either white or have a sunroof. Now I'm going to show you this with a table because I think the table makes it much easier to understand that overlap idea. So we have a couple examples coming up that'll show that. But that's the general rule. The general rule is if they are not mutually exclusive, we're going to take the probability of A plus the probability of B, and then we're going to subtract out the probability of A and B, which is the overlap. Okay, how much do they overlap? How much do they both share? So we're going to start with a deck of cards again. So the question is, what is the probability that a randomly drawn card is a heart or a queen? So here's all the hearts, and here's all the queens. So are those mutually exclusive events? No, they are not. This card right here in the middle, I'll put a big star on it, is both a heart and a queen. So these are not mutually exclusive because you can be a queen of hearts. There's one of those. So one occurrence of that. So we can't just say it's 13 hearts plus 4 queens, because if we do that, we double count the Queen of Hearts. Okay? So what we have to do is we have to say the probability of a heart plus the probability of a queen, and then subtract out the probability that it's a queen of hearts, that it's both. So it's a queen and a heart. So the probability that's a heart is 13 hearts out of the 52 cards. The probability that's a queen, 1, 2, 3, 4 queens out of the 52 cards. So 1, 2, 3, and 4. So here's our 4, here's our 13. But when we do that, I already counted the Queen of Hearts with the, I already counted the Queen of Hearts when I counted the hearts. So I need to take out that one overlap out of the 52. So in this case, it's 13 plus 4, which is 17, minus 1, which is 16 out of 52. Now, in my opinion, if it's very obvious like this, I prefer to tell you just don't count the queen twice. Say, well, there's 13, and then there's 3 other queens. I don't need to count that one. So 13 plus 3 is 16. So if it's something that's very visual, you don't have to rely on the formula. If you understand the concept of it and you say, well, I can see that if I count that, it's going to get double counted, and I know I shouldn't do that, it's okay to do that. So you have 13 hearts, and then after you count those 13 hearts, you want to know the probability that it's a queen, but hey, I've already counted this one, so I'm not going to count it again. I'm just going to count this one, and this one. So my 13 that I had for the hearts, plus my 3 additional queens that I haven't counted yet, and I get 13 50-seconds plus 3 50-seconds, which is 16 50-seconds. Okay, and then reduce, that comes out to be 4/13, which is about 0.308 or 30.8%. All right, so our last problem for this section, and then we'll call this it for this video. We have a two-way table again, and remember, these are totals. So 200 is the total number of students that were surveyed. 15 is the total walker bikers. 80 is the total cars. 105 is the total buses. 100 is the total juniors, and 100 here is the total seniors. So we want to know what's the probability that the student either rides the bus or is a junior. Well, are those mutually exclusive events? No, they're not. A student could ride the bus and be a junior. In fact, there's 70 of them. So, when we are looking at this table, I always tell students to do just like we did with the cards. Circle up what we have. So we want to know the probability that they rode the bus. That's these students. I'm not going to circle the total because I think that gets confusing. I'm just going to circle the cells that were the original cells. 35 bus seniors, 70 bus juniors. Then we want to know juniors, so that's all these students. And so what the formula tells us to do, the formula tells us to take the 105 bus riders out of the 200 students and then add the 100 juniors out of the 200 students, but then subtract out these 70 students that were bus riding juniors. And that would get you 135 out of 200, which is 27/40 if you reduce it, 0.675 or 67.5%. But again, you don't have to rely on the formula. If you can visually see it, and this is really, if you want to put like a big star by this is how I like to put it, the question on the exam, because I think it shows a better understanding than just memorizing the formula. And so I like to give a question like this on the exam in this version of a table like this. So my thought is, we don't really need the formula for this, and why would we count the juniors twice, the bus juniors twice, when we don't need to? So I would look at this and say, well, these 35 students are bus riders, these 70 students are bus riders, and then I want to add to that all the juniors. Well, I've already counted those juniors, so I'm going to only count these 2 more cells. And I would do this problem by saying 35 plus 70 plus 20 plus 10 students out of the 200 fit that criteria, and that comes out to be 135 out of 200. So I say, why count the juniors twice and then subtract them out when we could just not count them twice? Now, you decide for yourself. Some people really like to just stick with the formula. Other students, they're like, that makes a whole lot more sense. I'm going to do it that way. So you'll just have to decide on your own. Count these, then count these, and then just count the individual cells. 35 plus 70 plus 20 plus 10. All right. And that's it for 4.1 and 4.2, and I'll see you back for 4.3 with a continuation of probability.